So in this opening lecture, I want to provide some shared context about why we're here, the mathematical, experimental, statistical topics that we're going to discuss. I would say we come from several different backgrounds. Some of us are interested in AI alignment, some of us not to the same extent. But I think we can all agree that it would be better to understand learning machines much better than we currently do, including the formation of internal structure over the learning process. And one of the, I believe, very important applications in our time of acquiring such an understanding is to AI safety. So there's maybe three topics that together explain most of why we're here. Singular learning theory, SLT, is the first. So we're not going to provide a sort of detailed overview of SLT. I'm not presuming you've all watched every lecture of the primer or whatever, but at some point we move on. So the introductory stuff we did last time in Berkeley in the primer, those lectures are available. Many of you sort of have a working knowledge of SLT. If you don't, that's fine. So feel free to ask very basic questions to myself or Edmund or anybody around who seems to know what they're talking about. But I'm not going to cover sort of introductory stuff in today's lecture. I'll give a bit of a reminder of the story about phase transitions, which sort of informs a lot of what we're going to say. But SLT is a mathematical theory of Bayesian statistics, and it includes neural networks as in the class of learning machines to which it applies. A very beautiful theory developed over the last several decades by Sumio Watanabe, collaborators, students, and it's going to be our pleasure to have, I don't know if Mickey's here yet, but Aoyagi, one of the true experts in SLT from the Japanese school, will be here, and Hayashi is also going to speak near the end of the week. Developmental interpretability is something that we spoke about last time. It's an idea for studying the formation of internal structure in neural networks with a focus on phase transitions as the sort of core conceptual ingredient. This is new and much more speculative and not entirely founded on SLT, but also other ingredients. I'll say a bit more about it later. So SLT is this sort of older theory. Developmental interpretability is this attempt to use it to study the development of structure. And AI alignment, I guess I don't need to say much about. Okay, so we will often be referring to these three references, so it's worth spelling out what they are. The Grey Book is the original SLT textbook from 2009. The Green Book is the updated version in 2018. And of course, there are many, many papers by Watanabe and collaborators laying out all of this theory. But maybe one of the key turning points between these two works was the WBIC paper, and I want to flag what happened there because it actually matters quite a bit for the story about phase transitions. So in the Grey Book, there was an assumption of realizability, meaning that the true distribution is actually realizable by the model. There are many technical hypotheses in the fundamental conditions in this book, and you look at them and you're kind of like, oh, well, okay, maybe I never checked that, but probably it's fine. Realizability is a real restraint that actually restricts the generality of the theory. But through subsequent works, this was weakened to relative finite variance, which is the condition that you'll see in the similar statements in the Green Book. And that weakening is necessary for the story about phase transitions, which is kind of the place where maybe it has been the most significant progress in connection with SLT over the last 6 months. Okay, so we're here primarily, I guess, to try and understand what neural networks are up to. It's worth flagging at the outset that this is not like a solved problem. You just have SLT and suddenly you know that you have a theory of deep learning. It's potentially a theory of deep learning, but there are many unresolved questions, and I want to flag these very explicitly at the outset. In the open problem session, I'll maybe return to some of these, but I'm not even saying these are the four most important ones, they're just the ones that came to mind. Maybe I'll put them all up. Unrealizability, I already mentioned. It seems likely, especially if you're going to talk about RL together with SLT, that relative finite variance is like just palming off this question of unrealizability in this way is not going to be sufficient. Some of the deep issues to do with unrealizability may come back, and the theory needs to be extended in a significant way. That may also be true even in the neural networks that we're currently trying to study with the theory. That's an open question. The Bayes versus SGD point, I think, occurs to everybody the first time they see SLT. This is just the point that it's a Bayesian theory. It talks about Bayesian learning. The Bayesian learning process is where you see more samples and the Bayesian posterior does something. That is not a priori necessarily related to the learning process in the sense that you mean it when you train a neural network, right? When you just watch an SGD trajectory proceed over the loss landscape. Those two things might be related. They're probably, I mean, there are suggestions for how they might be related. It's an open question, the degree to which they're related. And also an open question, a degree to which this is actually critical for applying SLT. I'll come back to that. I think, Edmund can disagree, but I think our experience thinking about this over the last few years is that initially we thought this was extremely important, and we're sort of backing away from that in some respects. I'll explain why in a few minutes. Asymptotics, this was probably the key question, doubt, that I think it was sensible to have at the beginning of this year. So SLT, putting aside this for a moment, SLT, the main theorem, is the free energy formula, the asymptotic expansion for the free energy. It says something about what happens when you see in the limit of infinitely many samples. Does that actually work for the finite n being the number of samples, that you actually see in your machine when you're training? Well, that's not a theoretical question, it's an empirical question. And so setting out to actually see if that is, this formula actually works in real systems was one of the things that we were most concerned to do this year. Yeah?
I have a question. Has there been any work to extend what Ananda is first order asymptotics to an asymptotic series, to all orders?
Yeah, good question. No, I think that is currently gatekept on somebody with more geometry knowledge, carefully studying the asymptotics. Yeah, no, it's, I mean, we haven't made any progress theoretically on that. I think it's possible. Yeah, I can sketch what I think might be the way to do it, but so far that hasn't been done. Yeah. Well, any other questions about the points I've covered? Yeah.
So the free energy formula is written as up and low terms with, like with a bit of work you can look at low order terms, but exactly what those terms means
right.
might require more geometric knowledge in higher terms.
Yeah, the reason we feel comfortable speculating that it's sort of talking about more complex geometry is that in the minimally singular case where the KL divergence is locally a sum of squares, then we know what some of those higher order terms are due to classical treatments, and those have to do with information geometric quantities, curvature tensors, and so on. Yeah. So presumably there's, like if you make that story degenerate, you're talking about some sort of invariance of singular structure. Yeah. So that's probably deeply interesting. I think somebody should definitely work on that. Right now, it's not on our roadmap. Yeah. Yeah. The final point is, okay, suppose these are taken care of. Yeah.
You said the point of the asymptotics.
Oh, I didn't. Sorry?
I think you were going to say that empirically the asymptotics are reached.
Oh, that's the punchline. That comes later in the talk, Alexander. We'll set up the doubt and the... Yeah, but thank you. The final point here is, okay, I mean, even if that's fine and you're sort of in a regime of n for which the free energy formula applies, and this is not a fundamental limitation and this is okay, still well, how good is a theory if, I mean, you can't predict using the free energy formula if you can't independently actually estimate the coefficients in the formula, right? And this perhaps was very unclear prior to sort of like earlier this year or last year. Theoretically deriving the RLCT is very difficult. It requires very detailed knowledge of the geometry. It's unlikely to be possible, keeping in mind that the RLCT is data dependent. It's unlikely that you're going to be able to compute it theoretically for real systems. But I suppose we're gaining some confidence that it may be possible to estimate reasonably well or well enough learning coefficients. So that's maybe the biggest update to take away from the progress over the last 6 months. Okay, any further questions? All right. So as I said, I want to talk about phase transitions. I think this is the place where SLT seems to be saying the most significant things per hour of thought currently. This is the start of our study of phase transitions in SLT, this somewhat mysterious figure in section 7.6 of the Grey Book. I don't really want to talk about it. I just want to say that we've been staring at this figure for like a year, and maybe it's kind of understood at this point. And also to credit Watanabe for also flagging the importance of phase transitions, right? So we'll be presenting some experiments that are new, and I think we've made some progress understanding phase transitions, but really Watanabe foresaw everything, at least like in the theoretical form, that we're going to talk about, starting in section 7.6, which is maybe a bit cryptic, but definitely he understood how central the singular learning process phase transitions were. While I'm mentioning it, so section 7.6, the Green Book has a section talking about phase transitions, but not so much in phase transitions in N, although there are some examples there. And there's also a talk that I've cited elsewhere where Watanabe is talking about this. And so the treatment I'm going to give here is the theoretical parts are largely derived from Watanabe's treatment of this story. Okay, why phase transitions? Well, it's actually an open question to what degree phase transitions are really important in understanding neural networks and the structure that forms in them over training. The state we're in now is people have observed lots of interesting ones. I would say that still the best developed and most interesting example is induction heads and in-context learning in this paper from Anthropic. Maybe you should ask me later if you want to learn more about this paper. I won't go into details about why I think it's the most interesting example or the most well-defended perhaps. I'm aware that many people like the grokking example of phase transitions. Someone can tell me if they disagree with the following statement. I think this is very interesting and has inspired a lot of work, but is not what I think of as a typical phase transition. So I'm a little perplexed by the obsession with grokking. Yeah. So, I mean, I like those papers, but I think this is not like, an outsider might get the impression from the predominance of work on grokking that this is like...
It is a real phase transition, just not SLT.
Yeah. Okay. Are these actually phase transitions? Is a good question to start with. Sometimes people hedge by using terms like phase change. I think Olsen et al. Do that. So what do people actually mean when they say phase transition? Well, they mean a few things. Maybe just to put aside some kinds of phase transitions for a moment. So you can observe a qualitative change in the nature of the final learned solution if you vary the problem. Right? So you vary the data distribution, you vary something about the optimizer, and then maybe you retrain many times and you see that as you vary those hyperparameters, the final solution jumps to some other thing. That is not the kind of phase transition I'm talking about. That is a genuine phase transition, and that's also in some sense not difficult to put into a standard framework of phase transitions. The kind of phase transition that I'm talking about, and the one that's discussed here, is more like overtraining, right? So you're optimizing by SGD, and you observe that for many trajectories when you're training, that at some point, perhaps sort of at a similar number of steps, there's a discrete-ish qualitative change in the nature of the algorithm that is being executed by the network. That is what people mean by a phase transition. It often comes along with a sort of sharp drop in the loss, but not always. So in this case, if you look at the larger models that are trained there, once it gets up to on the order of 10 billion parameters, the loss curve, there's no like sharp thing like that, right? It's very, like there's some sort of little dip. So when people talk about a phase transition over training, it's not that it's necessarily some backwards S-shaped curve where the loss drops suddenly. It may be less obvious than that. But generally speaking, you would associate the term phase transition to these events in training if some other kind of metric that is measuring the kind of algorithm that's being executed, or which you believe is measuring it, does undergo such a sudden change, indicating so it's sort of like you're inferring that the internal structure has changed by some kind of measurement. Yeah.
I mean, if I think like a physicist, then I would care a lot about how the suddenness of these phase transitions changes as I vary the size of the learning machine.
Mm-hmm, mm-hmm.
Has this been studied systematically?
I think that's...
Can you repeat the questions?
Oh, repeat the question, yeah. So the question was, as you vary the size of the system, does that affect the suddenness of the transitions? I think that's related to the comment I was making, yeah. So as you, in this paper, they look at a range of systems, so transformers with different numbers of parameters. The bigger the system, well, the transition is kind of buried. It becomes less visible.
Less sudden.
Yeah.
So that's sort of contrary to what physicists might expect.
You're thinking about like a...
You somehow, in physics, in the thermodynamic limit, a first order phase transition should become sharp.
Yeah, but in that case, the transition sort of involves large-scale behavior that spans the new degrees of freedom that you're adding, right? In this case, I think the transition is sort of like the transitions in neural networks probably, they only involve some relatively small subset of the weights. Mm-hmm. So, yeah, we can talk about it later, but yeah, that's a good question. Anyway, it's not sort of obvious in what sense those are transitions. Yep.
Just to comment on that, I don't remember the paper exactly whether when they're scaling up the parameters, they sort of scale up the problem size too much, and if they don't do that, then this doesn't maybe quite map onto the physicist-style scale system up. So it's not clear if this is actually like maps to what we do in thermodynamics when we talk about the infinite limit.
Thanks. So I'm going to sort of circle around and come back to this question of in what sense are these phase transitions. But I want to flag at the outset what, from my point of view, is the key conceptual point, and what I think from the point of view of SLT is the way to think about what's going on here. So it's, I don't know, this, it's not visible on the screen. The point is that there is a kind of phase transition that's mathematically well defined in Bayesian learning. You can see that this is dominated by the singularities of the loss landscape or the KL divergence. And at the same time, those singularities you might expect, and in some cases can show directly, what dominate the learning process. So it's not exactly that there's a clear connection between phase transitions in the Bayesian sense, which I'll define in a moment, and phase transitions over training in the sense I was just sort of informally describing. Rather, it's that both are probably determined by geometry. At least that's how I would explain the connection right now. Okay, so I want to speed run through just the sort of setup of SLT and the language of phase transitions. I really mean it, so. Free energy, negative logarithm, the exponential. LNW is the negative log likelihood. In the special case where we're talking about a regression problem and we're modeling a joint distribution of inputs x and outputs y, and the probability model has this form, then the negative log likelihood by a simple calculation is just the mean squared error. So this is, W is the weights of your neural network in this case, N is the number of samples. This is just the mean squared error. F is the neural network with input X, weights W, and then some terms that don't really matter for our purposes. So it's kind of reasonable to think about LNW as being the empirical loss. And then L, which will come up at some point later, is the average over the data sets of Ln. So that's just the population loss. Okay, so the other objects in Bayesian statistics, so the free energy, the partition function, that's just related to the free energy by Fn is negative log Zn, also called the model evidence. The Bayesian posterior is the e to the minus n lnw divided by the partition function. Okay, so the key theorem to date in SLT is what we call the free energy formula. So assuming some conditions, including relative finite variance, which I mentioned earlier as a weakening of realizability, and some fundamental conditions, it's proven in the Green Book, making use of the work in the Grey Book, that there's an asymptotic expansion of the free energy given by a term that looks like the potential energy at some optimal parameter, a term that involves the RLCT or learning coefficient, the multiplicity, and then some lower order terms. Okay, so for the purposes of talking about phase transitions, and this was covered in SLT High 1 last time, so I'm just kind of giving you a reminder, I hope. We're going to focus mostly on the first two terms, although the lower order terms are actually seeming to be more relevant as we're looking at more examples. The point here is that model selection is kind of one of the basic conceptual organizing principles of Bayesian statistics. If you have two different models and you want to decide which is the better one to use to predict the future, you want to trade off accuracy against complexity. That's what these kinds of information criterions, or which is another way of thinking about what the free energy formula is saying, what these are for. A non-trivial prediction of SLT, as opposed to classical Bayesian statistics, is that this model selection process, which is usually thought of as a meta-activity that the statistician does, is actually a natural operation of Bayesian learning. And that happens internally to a given model class. So I'll sketch that in a moment, but we're going to take a triple P, Q, phi. P is the model, Q is the truth, phi is the prior, parameter space W. W alpha are going to stand for particular regions of parameter space, the precise conditions I don't want to go into now. We'll just refer to those as phases. So the alphas, the Greek letters, stand for phases. Okay, so let me explain what a Bayesian phase transition is. We imagine some collection of phases, W alpha, with some conditions, partition of unity, blah, blah. The point is we can split the integral of the free energy, right, which is negative log integral of the posterior over all of W. We use a partition of unity to split it into a sum over integrals over some subsets, W alpha. It's important to note that the W alphas have the same dimension as W. Right? They have non-empty interior. Just by this phi alpha is basically the original prior multiplied by the partition of unity. We're not going to worry about the role of that partition. It's going to drop out. Now, the point is to observe that this integral resembles the integral for the partition function of a model which has W alpha as its parameter space. The same true distribution and the same P, all right, because it's the same Ln here, and a modified prior, phi alpha. Okay, so if you take that submodel and you treat it as its own thing. It has its own free energy, which is by definition this integral. And so this is e to the minus the free energy for that submodel. Okay, and the observation is then, it's a bit of an awkward transition, I'm sorry. The point is that if you have an expression like this, which is log sum exp, then you would expect that whichever term here is the smallest as a function of alpha will, as long as the gap is sufficiently large to the other FNW betas, that term will dominate the expression. So this will look approximately like negative log e to the minus FNW alpha for that special alpha. And then the logarithm and the exponential and the minus signs cancel. And so what you get is that the free energy for the entire model looks approximately like minimizing the free energies of these phases over the alphas. And then you can apply the free energy formula to this FNW alpha and sort of just accumulating these lower order terms into something called C alpha, get an expression that looks like this.
This argument is very dependent on how you choose your partition unit.
Yeah, well, I mean,
how you coarse grain.
It depends on the n, yes. So if n is sufficiently large, the posterior mass will concentrate around like some critical point that dominates that W alpha, and the precise choice of the boundary doesn't matter, and the choice of the partition of unity doesn't matter. But if you're at a phase transition, and n is low enough that this actually, so this is one of the tricky points I'll get back to later, and Edmund will speak more about.
You are assuming also that the number of phases is finite.
Yeah, that's true. Yeah, good. Yeah, so I should say, like this, at this stage, there are many mathematical difficulties to making the story precise. So this has not been treated like at a mathematical level. This is kind of at a theoretical, yeah.
I was going to say, isn't it also possible that you have models that differ and you want to consider different phases that, like, no connected or something, and so, so you need to vary what position of you want that.
Yeah, absolutely. Yeah, so it may be that you choose a W alpha and a W beta, but really they're the same phase. And so you get a multiplicity in this sum, which is sort of not accounted for. Yeah, and so that's right.
I was thinking the other way around, which is that, like, they're the same phase geometrically, but like functionally they're in the same phase.
Functionally. Oh, you mean like these things that are connected by a symmetry, but they're sort of...
No, it's just like you can travel from one solution to another solution without the loss changing, but they're different solutions.
Oh, different solutions. Oh, yeah, sure. Yeah. Mm-hmm.
Yeah, also just wanted to mention, I think in practice, from what we can tell, that seems super common. Like, as in often almost any solution on a training set, you can walk to any other solution without sort of leaving the zero loss manifold, if you will. So it's sort of non-trivial, I think, from what I know, to define what these different subsets you want to partition into here actually are.
Yeah, I'll just summarize these two comments as being that it's not correct to think necessarily of the W alphas having to be different basins, right? They're different regions which contain essentially different critical points, but there's really no implication in anything I said that there has to be, like, when you pass from one to the other, you leave the level set. That isn't implied. Yeah.
I have a question.
Yeah.
So if you, for example, if you're trying to do this in a way that like somehow has good predictive parameter SGD, what is the temperature parameter? Surely it's not this temperature, right? So what is the correct temperature? What is the temperate? Yeah, like what are the parameters of these exponents?
What is the coefficient in front of them? Is that what you're asking?
Yeah, what is the temperature?
Yeah, this is a good question. I don't think so the question was, if you're talking about SGD, if you're trying to match the Bayesian story to SGD, there's many hyperparameters in SGD you might worry about, like learning rate and other things that would affect like the sort of effective temperature in the corresponding Bayesian story. Here there's no temperature. You can introduce, of course, a temperature, and that will affect it's related to the n, right? So there's like an interaction between the temperature and the n.
When you have energy, yeah, you have to have a temperature, right? You have to choose.
That's right. Yeah.
There's no kind of known default.
Uh,
We did some experiments, and it seems that the number temperature is actually very bad. it's way too low, right? And in most kind of interesting problems.
So I think, I mean, here we're just using temperature 1, like normalization updated. We haven't got
Ah, we're using normalization, I see.
Yeah. Yeah, these are good questions. I think they're kind of expert questions there. Yeah.
Maybe even more interesting would be if there's some kind of intrinsic definition of temperature from some understanding of this learning process. Like in thermodynamics, we have a way to think about temperature in terms of heat flow. Is there a similar intuition here? Like what would be the correct conceptual definition?
Yeah, I don't have a confident enough answer for it to be sensible to answer this in front of an audience, but yeah, good question. Okay, so the point here being that the free energy of the entire model can perhaps, and this is like not a question you settle entirely theoretically, but you could have the hypothesis that in real systems, this is a guide to what happens in the Bayesian learning process as n increases, is that it shifts from some regions of parameter space to others as a function of the accuracy, this term here, and the complexity, which is what you conceptually associate to this lambda alpha. I haven't really defined lambda alpha, but that's the learning coefficient for this submodel. I'm not going to define the RLCT or the learning coefficient. You can just think of it as such an asymptotic expansion exists. If it exists, then there's a coefficient of log n, and that's what lambda alpha is. Of course, it has other interpretations. Okay, yeah, how am I doing for time? Maybe I'll just skate straight past this. Sorry? Halfway? Okay, that's fine. Yeah, so what is a phase transition then, in this sense? Well, if you think about the Bayesian posterior as something like a Boltzmann distribution, a first order phase transition would just mean, as n varies, that the sort of minima of the free energy which is preferred changes. Okay, so in this example, that is, you sort of have a situation for some n less than n critical, where the free energy of the phase W alpha is lower than Fn W beta. That means that W alpha is preferred. It wins the log sum exp competition. And then at some critical n, they're approximately equal, and then it switches. And in the case, there's sort of a distinction between whether this is actually the phase that dominates the entire posterior, meaning that this is the lowest among all possible alphas, but I'll just not dwell on that. Okay, so that's sort of what it looks like. If the free energy formula is a good description of what the posterior is doing, meaning perhaps that you're in the right range of n for that to be appropriate, and you've chosen the partition, you've chosen this decomposition into W alphas correctly, etc., etc., then you would expect that if this happens, then the actual posterior, if you could somehow magically just see it, would jump from one region of parameter space to another. That's what we mean by a Bayesian phase transition in n. Okay, I do want to show this calculation just to illustrate somehow the power of the free energy formula in deriving very simple predictions about how these phase transitions work. Okay, so L alpha meaning the accuracy of phase alpha, lambda alpha meaning its complexity. Okay, if we want to see where a phase transition takes place, we solve this equation to find the critical n, if one exists. Okay, you rearrange. You find that the critical quantity here is delta lambda, meaning the final lambda minus the initial lambda divided by the final energy minus the initial energy. That's an increasing function, so as long as that is positive, then it's possible. Yeah, there's various caveats. I think I'll leave those for Edmund's talk. And that's what it looks like if you plot the free energy at the phase transition. It swaps. The lowest one is the one that's dominating the posterior, and it swaps at this point. Okay, so that's what we've been referring to as a type A transition. It's the simplest one. It's where the energy decreases and the learning coefficient increases. And to cut a long story short, we sort of have good evidence that this actually occurs in practice. Somewhat more mysterious and interesting are, I mean, once you have an asymptotic expansion, you can consider the cases where some number of terms are sort of stable, and then you can talk about competition between the new leading order term and the sub-leading term. Okay, so a type A transition is where both the highest order term, the energy, and the second order term, the complexity, are in play, and there's a trade-off between them. But you could imagine that the energy at some point becomes stable, and then you could imagine trade-offs between the second and third terms. The third terms, meaning these constant order terms, are less well understood, but this is just kind of heuristic argument that I gave back in June for what we refer to as type B transitions. I apologize, I didn't fix this. This is an L. It's the accuracy. So if the energies are the same between two phases, but the sort of that grab bag of all the lower order terms, C, alpha, if those have the property that they are different, then you can solve to find that it's possible for there to be a transition, which we refer to as type B, which decreases the learning coefficient and increases the subleading term. Yep.
Sorry to be so
no, please.
physics-minded, but here the size of the network is fixed, right?
Correct, yeah.
So you don't even show it as a parameter.
The size, yeah.
But the physicist would be very interested in the specific heat, right? So everything depends on the size of the network, so I would like to understand the partial derivative of this free energy with respect to the size of the network. It would be like analogous specific heat. So if you ask, for example, about stability of the subphases, which I think would be very interesting, crucial to understanding to what extent these behave like phase transitions, you are essentially asking whether the specific heat is positive.
Well, I think there's a bit of a disanalogy with the physics setting, because you don't actually imagine that these phase transitions aren't involving like every parameter, right? So, like if you have a sufficiently large network, it might be.
To what extent these transitions survive as you vary the size of the network. And for this, specific heat is crucial, right? You want to know if it's convex and things like that.
Yeah, I don't know. Yeah.
I mean, it depends on how you sort of define what your large limit is, where I think I would agree that I'm a bit suspicious of defining it as just I scale up the number of parameters in the network without also scaling the size of the problem. Because then sort of, I would kind of expect that the effective number of parameters that are needed for the solutions of the RLCT learning coefficient thingy is actually going to stay somewhat constant. And sort of, you're just basically adding in parameters that aren't used.
But I mean, I think in any case you agree that the dependence of parameters is somehow crucial.
But this is actually a finite network phenomenon, right? This, I mean, like maybe a better, like the term that you use in physics is this is a symmetry breaking phenomenon, right? Where you have like a statistical theory with like one minimum, right, and then like it switches to, like in classical field theory, right? Sorry, if you have a classical field theory with one minimum and then it switches to a different minimum, that's kind of a symmetry breaking. They can happen even for a finite.
If I insist on having some kind of
and of course it only happens as the temperature goes to zero.
Of hope for a universal description of this phenomena, I will have to take some kind of limit in the parameters. It's very unlikely that you'll find a universal description unless you take some kind of limit in the parameters of the data, the size of the data and the size of the network. So somehow I'm very confused by why this isn't considered like a critical thing to check.
I believe, I think it is. Yeah, but how many people are actually doing this right now, Colleen? The people in this room.
Enough computing power to actually check.
Well, I don't know if it's a computing, maybe it's also a computing problem. But let's come back to that. I think those are excellent things to talk about in the open problem session. Yeah. Okay, so the point I want to make here is that just by doing this elementary mathematics on the free energy formula, you maybe believe in something that's a type B transition. At the time of the June meeting, I don't know, the night before, I thought about this and put it in the talk because it seemed kind of cute. But maybe they're actually real. So we're not sure yet, but you'll hear something about this in Jesse's talk later in the week. Okay, so I want to give some updates on what we've been up to. This is an old story, right? This is just a refresher. So I want to give you an update of what we've been doing since June. Here's a few projects we've been working on. I'm going to sketch what happened in all of them, and there'll be more details in subsequent talks. There was a project with Edmund Lau, myself, and Susan Wei, which is on the archive, Quantifying Degeneracy. This is where Susan had the idea to take the WBIC formula and combine it with SGLD and get some estimator of the local learning coefficient. And to our surprise, continuing surprise, I think this isn't complete garbage. Yeah, that's obviously a flippant comment, but I want to emphasize that it's not obvious at all that you can actually estimate RLCTs. So maybe it stops working for larger models, or this just isn't a very good tool in the end, but it's astonishing that it at least remains astonishing to me that we've gotten as far as we have. So I think that's really quite a surprise. TMS1, I'll say a bit about. Edmund's going to speak about that this afternoon. That's where we went looking for evidence of Bayesian phase transitions in a real system and found it. That's also in the archive. There's an ongoing project about in-context learning and sort of the SLT of in-context learning with the authors you can see listed in there. Jesse will say a bit about that later in the week. I want to flag some of the other things we're doing just because some of the people are here and then you'll know something to talk to them about. So Zach and Edmund are thinking about better ways of doing some of the stuff in the Quantifying Degeneracy paper. There's a follow-on paper from TMS1. I apologize for the acronyms, but this is just how we talk about them and you're going to have to suffer through our code language. So TMS2 is the follow-on paper, and that's looking at the story around catastrophes and its relation to this. I'll sketch what I think about that in a moment. I think it's quite critical, otherwise there's sort of like several confusing points about like what do you even mean by phase transitions if you don't understand that story. ICL2, we're sort of looking at in-context SLT. And there's vision and language. Sai and George are here and they're working on using some of these ideas to study vision models and the original induction head setting and language models more generally. This is a little bit different to what I'm going to cover in this lecture. I'll say a little bit about it at the end, some ideas for a principled way of answering the question of, well, what kind of geometric structure do we expect to find anyway if we could suddenly solve all these problems and look inside a neural network from an SLT point of view and just read off the precise geometry? Like, how would that tell us anything about what it's computing? There's some ideas for how to make some progress on that from a sort of logical point of view. Okay, so very briefly, Quantifying Degeneracy 1. We looked at earlier the formula that the free energy asymptotic expansion for a region gives you this local learning coefficient. That's a kind of measure of the model complexity of that region of parameter space. As I mentioned already, it's difficult to theoretically compute these values, and I've already mentioned that. I want to distinguish between local and global. This remains probably completely hopeless, at least as far as I can tell, right? There's just no reason, I think, to expect that you're going to be able to do good global sampling from something like the Bayesian posterior. There's no real reason to believe in SGLD in any situation. It's kind of amazing that it works even locally, but there's certainly no reason to believe in SGLD as a global sampler from the Bayesian posterior. That's just kind of fantastic. So I don't think that this is, certainly we have no ideas for how to do this. I'm quite skeptical that...
You know it apply people as NP.
Sorry?
If you could do it, you would apply people as NP.
I hadn't thought about that, but yeah. Yeah, that's a nice way, yeah. Okay, I think I see what you're saying, and I'm going to use that. That's nice. Oh, good, but we can do it locally, or at least we can try to. The idea, as I mentioned, was to make use of the WBSC formula and SGLD. Okay, I think given the time, I'm not going to talk about this because Edmund's going to cover it, but the upshot is that using SGLD, you can get some kind of estimate of a local learning coefficient. In small cases, it does actually compute something close to the independently known theoretical values. In general, we have no idea. Nobody knows what the RLCT, local RLCT of an MNIST model is. But you can run it on larger networks and get results that are at least consistent with some independent knowledge of the comparison of model complexity. So that's like a sanity check that this thing that you can run more generally does actually give somewhat sensible answers. I would say that the work that Nina and Dimitri have done recently, which many of you are familiar with, is also a very nice illustration of this local learning coefficient as being an indicator of model complexity consistent with like some other independent knowledge you have about what the complexity is. I don't know, are you guys speaking about it? Good, yeah, thanks. Okay, the question, so I'm going to dwell mostly on this paper, TMS1. Does this internal model selection process actually happen, or is it just some theoretical thing? And if it does happen, do the phase transitions actually work? I mean, do they actually sort of happen at the right n, or roughly the right n as predicted by the theory? It's sort of not easy to find good examples of this for a few reasons. You don't want an example that just has phase transitions, because if you don't have independent ability to say what the RLCT is, you can't actually check if the theory is working, right? So the desiderata for finding an example that is a good test of this phase transition story is that you want to be able to do MCMC sampling to really understand the posterior and see that actually the theory is working. For small n, that's not going to work very well because the sort of effects to do with the choice of W alpha are going to dominate the whole story, and it's just, I mean, you don't also expect the free energy formula to really tell you what's happening in the posterior for low n because it's an asymptotic formula after all, right? If n is too big, well then your MCMC sampler is just going to die. So you actually need the phase transitions to exist in a range of n that you can actually experimentally probe. That's non-trivial. You want a situation where you actually know some theoretical local learning coefficients, and you want this quantity to be relatively small so that you can actually catch several phase transitions, because this sort of tells you the gap in the critical ends. And we actually were looking for systems for quite a while before we sort of decided to take a look at this one, which was developed again by a group at Anthropic in 2022, where they had observed what I was calling earlier phase transitions over the course of training, in SGE training. And so it was natural to speculate that we would also find phase transitions in N. And so this is a nice video of the training process for one of these toy models of superposition. I'm not going to explain this system in detail, so this is kind of a bit of a I'll hand wave at some ingredients in this video. Edmund will say more about the exact system this afternoon. This is a visualization of the neural network. So the neural network is a matrix and a bias. So the weights connecting the nodes, a 2x6 matrix. And here you see visualized 6 vectors in 2 dimensions, so you can guess how that works. So those are the 6 vectors. There's a tiny one there. So that's the weight matrix visualized. The bias is not important for the moment, but it's given by the values you see on the top right there. And so this, what you see in this video is the neural network training. You see it's dropped the loss and dropped again in a moment. And those drops correspond to qualitative changes in the structure as visualized in the top left. That's one of the other things you want from an example of phase transitions. you want actually to be able to look at the network in some fashion and understand what actually happens in the transition. Mostly, so that you feel like you've understood the content of the transition. And the point perhaps here being that, again, this green curve, which is the local learning coefficient, is reacting to the transitions in a way that is consistent with what I was saying earlier about type A transitions, right, where the loss drops and the complexity increases. Although I don't want to say that it's obvious that this has anything to do with a type A transition a priori, right? Type A transitions were about the Bayesian posterior doing something. There's no Bayesian posterior on this slide. This is just SGD training. Okay, but still, the fact that in these observed events that happen over the course of training, the loss drops and the model complexity increases, well, there's no obvious learning dynamic principle sufficiently general to guarantee or even give some sufficiently convincing reason why this model complexity measure must increase when such an event happens, right? Independent of some connection to SLT, perhaps. Okay, yeah, I don't want to spoil Edmund's talk, but the correspondence between these two plots, this is a theory plot of the free energy formula, this is an MCMC plot. For low n and high n, they kind of disagree in various ways, but there's a region of n where we can sort of independently check that the sampling is good, and in that region, indeed, the theory and experiment both agree that there's a phase transition between a particular configuration, which we refer to as the 5-gon, and another configuration, the 6-gon. So I would view this as an experimental verification of the free energy formula actually working in a smallish range of n, in this case around 600, and phase transitions of the Bayesian posterior actually happening in systems that have independently arisen in deep learning practice. Yeah, this thing at the bottom is a T-SNE visualization of the transition that Edmund, I think, will talk more about. Okay, so there's well, maybe, are there any questions?
How robust is this and the changes of nonlinearity?
Yeah, good question. I have no idea. I mean, this paper has many interconnected parts, and the theoretical parts required just very lengthy calculations with a particular loss function, which are highly dependent on the particular nonlinearity. Now, I would say that the connection between, if you change the nonlinearity, we stop being able to compute the theoretical RLCTs that allow us to make this plot, so this goes away, potentially. Then, well, maybe you can estimate the local learning coefficient and then see if it corresponds to the MCMC sampling, but nobody's done that, so, yeah.
I was just wanting to emphasize that you said that the specific experimental verification we're doing here is not anything of SGD or some theory that we know SLT works in, specifically that this seems to match up in the non-infinite end case, right?
That's right. Yeah, thank you. Yeah, just to repeat that. So what I'm saying, asserting, has been checked experimentally on this slide is nothing to do with the correspondence between SGD and the Bayesian posterior. It's purely about the question, the SLT internal kind of question about whether the free energy formula really applies at finite n and whether phase transitions in the Bayesian posterior happen. The relation to SGD is a separate thing. Yeah, thanks. Okay, well, talking about the relation between SGD and Bayes, here's one way of, it's a bit too naive, but it's a starting point. To come back to this argument that the reason you might expect a relation between these phase changes over training and the kind of phase transitions that are genuinely phase transitions in SLT is that both of those things perhaps have a common source, which is the critical points that the trajectories pass near over the course of training. This is meant to be a cartoon of an SGD trajectory. Steps on the x-axis, loss on the y-axis. There's some kind of plateaus, and it drops between plateaus. Now, it's only for very small systems I think that you expect to see like some very clear staircase like this. Larger systems, if it's visible at all, it'll be like kind of either many of them, or they'll just kind of be pretty hard. Like it spends almost no time really anywhere near the critical point. Still dominates the trajectory in some global sense, but it's not nearby enough to sort of get stuck near it.
This is exactly spontaneous symmetry breaking, right?
Spontaneous symmetry breaking is a very specific kind of passage near a critical point. Not all these will be spontaneous symmetry breaking.
The standard generalization.
That's right. Yeah.
Stochastic gradient descent. So this is really a stochastic process, right?
That's correct. Yeah, that's right.
So it's a bit like a stochastic sampling of what you're saying.
Okay, so if in this case there are 3 critical points, the trajectory passes nearby, and you have plateaus corresponding to them, you can sort of play the following game where you go look at parameter space, you find that critical point, it's called a W alpha star, you just invent some region around it, suitably chosen W alpha. You do the same for the second critical point and the third. And then you can ask the question, well, is it true for some n that the posterior, the Bayesian posterior, is sort of concentrated near here, and then jumps to being concentrated near there for some larger n, and then jumps again? And if that were the case, you'd sort of have some kind of coarse-grained correspondence between the behavior of SGD trajectories, where they're sort of like dominated by this, then dominated by that, and what's happening to the posterior, which is dominated by this and then dominated by that. As I said, this is too naive, but like this is a starting point that's not crazy, right? Okay, so we refer to these as Bayesian transitions and these as dynamical transitions. Well, we can ask the question in TMS1, well, what is, we can just go and look at trajectories and see what happens on the left-hand side, and we have some understanding of what's happening to the posterior because of a classification of the critical points. So we can ask what happens on the right-hand side. And the sort of relation between the two is a little bit subtle, but I think this is probably the most interesting figure in the paper and one of the things that points in many open directions. So it's one of the things I want to advertise for this week. We have no real idea why this picture looks like this, but it's pretty interesting. Let me explain literally what it is before I say why it's interesting. So on the x-axis, learning coefficients. It's a bit mislabeled. I apologize. Well, I'll come back to why it's mislabeled. The y-axis is the loss. So we have loss, learning coefficient. The points are critical points corresponding to phases or regions of parameter space. They're labeled by some classification scheme that I won't get into. So each one of those points is some potential phase. The error bars indicate estimated local learning coefficients. The red lines here are observed dynamical transitions. Okay, so a red line between two critical points, say from 4 plus plus minus to 4 plus, indicates that in some one out of, I think there was like on the order of 400 or 500 SGD trajectories, maybe more. In some trajectory, a path, an SGD training run was near this, and then at some later time near this critical point without passing nearby any other known critical point.
Obviously that frequency depended on initialization, right?
Yeah.
Initialized on the square, it was not all common.
That's right, yeah, so there's, it would take quite a while to elaborate like the exact conditions that produce this, and I'm glad for Jake for pointing out that there is real content to those choices. So if you're serious about paying attention to this diagram, you need to understand those initializations. Yeah. Yeah.
So if there's no line out of 4, does that mean it never left 4? It got stuck
Correct.
there?
Yeah.
Are these all the critical points?
We don't know.
So this doesn't give you the right cohomology, right? Because it's disconnected from the if you view this as I guess if you assume that all of these critical points are non-degenerate, and so this computes actual trajectories.
Oh, they are degenerate. Yeah, yeah. We don't know that these are all the critical points, but these are, I mean, out of many initializations of SGD, these are the only places where trajectories end up. So I guess we feel somewhat confident that at least at low energy, these are the only ones.
I see, but there might be some high energy critical points.
That's right.
And that could be very common.
Yeah, they are definitely high energy ones.
Okay, I see.
But then we have some theoretical reason to believe that there isn't anything else that fits inside within these low energy ones.
I see.
And the other evidence is that MCMC sampling and SGD trajectories that we see are all classified into these ones. So not definitive statements, but rather confident.
Yeah, well, since you asked about 4, yeah, so not only do you never see a transition from 4 to anything, but you notice something quite interesting about the transitions that do occur. I mean, you don't understand what these labels mean, but you can see that a plus minus can cancel. Plus plus minus plus. Plus minus minus 4 minus. Okay, so we don't understand exactly what is going on there, but the broader point is this is not unusual. Like, this is what a physicist would call a selection effect, right? So there's some symmetry we're not understanding, or some constrained quantity that is actually meaning that not all the transitions that are allowed by like a free energy calculation can actually take place dynamically. So for a transition to be dynamic, so think about in chemistry where you have like a Gibbs free energy and you say, well, a reaction can only occur if it decreases. Doesn't mean that the reaction has to happen. There might be some other reason to do with the details of chemistry why that just can't occur, but it's a constraint, right? So in this case, moving down and to the right means that the energy decreases and the learning coefficient increases. So from the point of view of the free energy formula, any passage that goes down and to the right is like a potentially thing that could happen, but not all such potential things do happen. So the relation between dynamical and Bayesian transitions is not, it can't be like a one-to-one thing. Yeah.
So, question on the labels. Like, did you label these in response to this picture, or did the labels come from somewhere else and now you're observing that? The
plus and minuses, you mean? No, that just came from the nature of the classification. So if you look at it, I mean, the plus refers to a bias that's positive and a minus refers to a bias that's large and negative. So it's like, if you get really into the weeds of how this potential works, then you come up with this classification.
So, and in this picture, are you confident that there are no other Morse trajectories between these? Like,
yes.
So then there has to be a hierarchy. Actually, even if these are degenerate, like this is still not the right, this can't be the right cohomology because it'll be disconnected, so there has to be.
Yep, I agree.
Yeah, so 2 questions. I think the first one is, it will be interesting to see the generalization behavior of these critical points, like specifically like what happens if we test outside the data points that these been trained on. So it'll be interesting to see like why it gets stuck in 4, for example, and whether this then affects like how well the solutions that you can get from this, like in theory, like are even possible. And this can like relate to like why certain architectures better than others for certain problems. And then my second question is like, you made a very good point about like how free energy cannot tell us everything about whether a system will actually go through a certain like change. In particular, in chemistry, you have like the free energy view, and you also have like the kind of more dynamics view kind of thing, saying like, okay, well, in theory, it's like spontaneously possible, but the rate at which like these like the actual particles that need to react kind of come together is like very, very low, so like, this is not going to happen. Is that like an equivalent kind of model here?
That's how I think about it, but I don't know like the extra information that you're adding there to the free energy, which would allow you to reason about the reaction, is not really present in this story.
What would be the chemical?
Okay.
Pros having discussion for now, so let's wrap up the talk, and then we'll swap the discussion and the activity so we can continue.
Yeah, okay, let me just check, I'll come back to this and I'll just finish some slides. I'll just skip over this and do it some other day. Okay, yeah, there was a lot of slides. Okay, but this one I actually want to fit into this talk because I really like this. Watanabe gave this really lovely short talk at the last meeting we had, and I recommend you go and watch it if you haven't. He put a lot of thought into the problem of AI safety independently, and he made the point that one of the key things to be done at this stage is to, yeah, I kind of like the way he wrote that, is to take problems in AI alignment and actually figure out precise problems that can be solved by people outside of the field, making use of their own specializations, right? There are a lot of mathematicians, physicists. I mean, a lot of you come from those backgrounds, right? So you're like sitting here in the room, but there are also people out there who are just off doing those disciplines, not knowing that they could potentially contribute to AI alignment. But as we make progress on actually doing this translation, orders of magnitudes more people can start to contribute and actually want to contribute, but right now don't know how to do that. So I would encourage and think one of the things we can do this week as some of the people who have actually made an active effort to be on this boundary is to do some of this work together. So that's an activity I'd like to recommend. The rest, I think, yeah. Okay, but I want to wait. I want to end on a cryptic quote. Okay, now you can clap. Thank you.